This conference will now be recorded.
So, dear students, good morning to all of you. So far, we have discussed distillation operations and also at length the McCabe-Thiele method and the Panchen-Chavaret methods have been discussed. And its analysis is required for various special cases, and that I will do in one of the tutorial, so that I can also conduct one slip test during that period. So you please wait that. But today I am going to explain you all the new concept, that is the liquid extraction. Okay. So all of you might be aware of from your process calculations what is the liquid extraction. So liquid extraction is having another name, that is also called solvent extraction. So it is the separation of the components based on its solubility. If you take one of the solute which may have its solubility in different solvents, and let us call solvent A is having solute which is named as a C. So A is having C, then we require B solvent which is which can get dissolved the C component in it, and therefore it can be separated. So however, we should see the density difference between the A and B so that we can easily separate. So initially we should have a mixing, then you have to separate them. So C in fact will be exchanged between the solvents A and B. So finally they reach to the equilibrium. Since there are two different distinct liquid phases are existing, then it is called liquid extraction. Once the separation is completed, how do we know that separation is completed? That is, the equilibrium is attained, then we can separate one layer from another layer by using the decantation technique. So therefore two layers will get separated. One layer will have less quantity of C component, other layer will have maybe a little more than the A phase. So B phase is usually you can say it is a useful, and it is a product, because which is removing the C component from that, then depending upon the operation you can call it as a product. And A phase which is left over with a small quantity of C is called residue, as you have defined in case of the distillation operation.
Sir, hello. You are not audible, sir.
This conference will now be recorded.
So as I was explaining you, the liquid extraction is one of the important operation in chemical process industry, and also it is a energy intensified operation where you may not require the that much of energy which is usually used consumed in another operations. So as I told you all of you that the one minute, yeah, uh, uh, that the one of the component will be exchanged between the two different phases which are typically immiscible in each other. Maybe certain partial miscibility might be there, but however the component which we are calling as a C, that is a solute, will be miscible in both the phases, and it makes equilibrium at a certain concentrations between these two phases. Therefore, the liquid extraction is also the equilibrium operation. So you just think that in the distillation, due to the its relative volatilities, the separation is done. Here, due to the relative solubilities, the separation is done. The difference in the solubilities of different liquids of a particular component will allow us to do that. For example, you can say that acetic acid, which is there in water, so it can be separated by using the distillation column. Now, when it is able to separate by distillation, why you require liquid extraction? So that question arises. Acetic acid water, if you look at its alpha value, relative volatility value, that is very close to 1. So you know what happens if our relative volatility is very close to 1, then the equilibrium curve, XY curve, is very near to the XY, the operating line. So that means it requires more number of stages. So when it requires more number of stages in a distillation, then the fixed cost will be very high. And the fixed cost is very high. And also we should look at uh, the condenser as well as the reboiler. So when you compare this condenser and reboiler as an ancillary units for a distillation column, so their uh, capacities also should be very high due to the alpha value is very close to 1. Therefore, instead of doing the distillation, if you do by using the liquid extraction for separation of acetic acid from the water, so that will be more economically feasible. So therefore, so in certain cases, the liquid extraction will replace the conventional distillation operation to reduce the consumption of the energy requirements as well as other fixed costs and operating costs. So since there is an equilibrium between the two different dense phases, so you can say that this is a very easy to separate. In certain cases, you know, all of you know that density difference may be very close, and we'll see whether such type of solvents are selected or not. If you go into details of the actual process, so this process indicated by these diagrams, you can see here the bottom one is which is in orange color is called feed solution. So usually in feed solution will be I'll give you number of examples. The water which is contained acetic acid, so you should remove the acetic acid for the various purposes to recover the acetic acid which is going into the going along with the water stream for the recovery purpose. And another purpose is you have to treat the water for the removal of the acetic acid, because acetic acid is polluting the water. So that is the one case. Such cases are many. In many chemical process industries, the requirement of the liquid-liquid extraction exists because of the thing that either you want to separate the component which is escaping from the one of the stream, or you want to uh, treat that stream for the removal of that particular component. So both the cases, in one case the recovered solute is very important. In another case the removed, you can say that washed out the liquid phase is very important. So many examples if you cite, and aqueous layers. Aqueous layer means water is the major component, and it may contain some of the components. Usually acid will be the one of the component in which you adopt the liquid extraction. Therefore we call water plus acid is an aqueous layer. So this aqueous layer will be treated with solvents which are organic in nature. Therefore, the phase which you brought in contact with water phase, aqueous phase, is called organic phase. And this organic phase and aqueous phase both will be mixed in a mixture like this, which is shown in the second diagram, and where all three components will be mixed together. Three components means one feed solvent, that is water, and another is organic solvent, that is any organic solvent which you use starting from the chloroform, and there are number of solvents which can be used. And another one is the acetic acid, or carboxylic acids can be used there. So you have a three components. One feed solvent, you can name them feed solvent, which will be there in the feed with the C component, that is the solute. You can name that solute, which is active component, which will be exchanged between these two phases. And the third one which you are adding for the purpose of separation is organic solvent. So that is called extracting solvent. Feed solvent, extracting solvent, the solute which is getting distributed among these two phases. So this terminology is used. So all will be mixed in a mixture. You can design this mixture, then it will be sent to the phase separation. So phase separation will be done in a decanter. So it is based on the density, because there is a immiscibility between the organic solvent and feed solvent. So it will be settling like this. Once they settle, then you remove two different phases. So the aqueous phase, in which non-extracted solute is there, because not all the solute will be extracted. So that layer is usually called raffinate. This is the industrial name. Raffinate will be obtained as a residue. Then another one is the blue one, in which some of the solute molecules already dissolved is come out with solute. Then we will call that as an extract phase. Then you can say that if you just look at this particular operation, we will add feed to the solvent, and finally you will get extract as well as the raffinate. So this is how we should understand the operation. Okay, it is clear. So there will be three components always in the system. All three may be there in all the phases. When you add, or before adding, there may be a one solution, feed solution, and solvent may be pure. You can't say that it is having a C component, but it will be added here. Once you add in the system, you have three components. So three components are mixed together, and one of the component will be exchanged between the phases. Then they will be settling into the two layers due to the density difference. Only gravity only work, because you have to select the solvent such that it should have a sufficient density difference. So density difference will give you two layers. Then the two layers can be separated as extract and raffinate. So the inputs are feed, solvent, outputs are extract and raffinate. But you should use two different unit operation. One is mixture and another is settler. So mixture and settler will make a single unit operation and a single stage where only certain separation of the C will occur. Again, this raffinate, if you are not satisfied with so much of solute is going along with the raffinate without extraction, then you can send them back into the another stage. So you can add again solvent there, then again it will be mixed, and then the separation will be phase separation will be taking place. So it can also be done in a stage wise. So multi stages can be used for the better separation. Okay, so this is the operation where you will get the extract layer, raffinate layer, or organic layer, or no aqueous layer. So you can just think about that. Then why this liquid extraction is required? As I told you earlier, when difference in boiling point of two component is very low, that is the alpha value is very low, or bubble point and dew points are very close. If they are equal, then there is no separation, because you know it is called azeotropic mixture. Then very close, then the separation expenditure will be very high. To reduce that one, you can do the liquid extraction. Or if azeotropic mixtures, or azeotropic mixtures means alpha is equal to 1. For such type of mixtures also, you can use liquid extraction, and there you can do certain separation. And the third one is to avoid the thermal decomposition. This is a very important aspect in some of the components. As you have seen in the steam distillation, you are not heating the component because its boiling point is very high, more than the water boiling point. Then when you are heating to that particular point, then what is happening? There is a thermal decomposition, or charring is taking place, or combustion is taking place, or sometimes explosion may occur due to the high temperatures. So to avoid that one, we are adopting the steam distillation. But in the steam distillation, again you have to use the steam, and the temperature would be 100 degrees centigrade. It will not come below the 100 degrees centigrade. It is very near to the 100 degrees centigrade. Then that also requires certain energy. So to avoid all these things, and also to save the thermal sensitive components without getting exposure to the high temperatures, then liquid extraction can be done. So that is another aspect. Then also I have from the beginning telling you that it consumes lower energy than the distillation. Lower energy means some cases, only to operate the mixture and settlers. If the settler is a centrifugal settling equipment, if the gravity settling means you don't require any energy. If it is a centrifugal settling or centrifugal separator, centrifuge, if you want to use that, because of the density difference is very close, then you should require certain energy. Otherwise, energy requirements is almost zero in case of the liquid extraction. And the fourth or fifth one, if proportion of one component is very less than other, and it have high boiling point. So this is also an aspect. See, one component is having very high boiling point, and another component is a low boiling point. It can be separated very easily, but its proportion is very low, very low. If the proportion of one component is very low, very less than the other, and it have high boiling point. For example, low proportion component is having high boiling point, then it is the conventional distillation is not advisable. Then you have to go for the liquid extraction. Okay, so these are the certain reasons why liquid extraction is required. Then you see the separation is done in the liquid-liquid extraction according to the different in solubility. So that you understood so far. Then the problem with the liquid-liquid extraction that we mix, then we separate, should be focused, and also we should have such a unit operation which is called extractor, in which these two operations should be together, and you should have a intensified unit operation where the mixing and separation is done simultaneously. Such a equipment you should look at for the liquid-liquid extraction operation. Initially the phases should mix each other, then they will get separate. So the problem with liquid-liquid extraction is mixing and separation. Okay, so that we'll see, we'll understand once you complete the principles of liquid-liquid extraction and how to design an equipment which will have both the mixing as well as the separation. Okay, where it will be useful, as I told you, again I will just repeat them. Applications of the liquid extraction fall into several categories: those where extraction is in direct competition with other separation methods, and those where it seems uniquely qualified. In certain cases, you see, no other separation method works out except extraction. As I told you, some of the cases where alpha is 1 azeotropic mixtures, then the distillation will not work. So this will be easily done by the liquid-liquid extraction. And in certain cases where indirect competition means it reduces the cost, and it reduces the chemical consumption, it reduces the energy consumption, therefore the cost will be reduced. So as a alternative method, you can take up the liquid extraction. So these are the three important aspects where you can prepare the liquid extraction in competition with other mass transfer operations, as I explained earlier, as a substitute for chemical methods. See, in certain cases, you might be seeing that in metallurgical industry, to extract metals from the earth crustals, once the ore is processed for the removal of metals, and certain metal residues may be there in the cluster of the ore, so that you usually call it as a trails. There will be left over there, but in certain cases they will be having value added metals. So to remove that value added metals, what we do is we will be just uh, taking them and reacting with some of uh, the base materials, then we'll get salts, and the salts can be again subjected to the recovery of the metals. So this we usually do that. Instead of doing that, if the minerals which are having this value added metals, that can be treated with acids. So in the acids the metals will be soluble, then that can be removed. So that is a substitute for chemical method where to save the consumption of the chemicals, etc. And also for separations not now possible by other methods. So this also I explained. So all in all, these are the certain areas where liquid extraction will be used as an alternative method. So now coming to the certain basic principles of the liquid extraction. So in the liquid extraction, as you have seen that there will be three components. The component one is feed solvent. A is usually called feed solvent, and B is called uh, the organic solvent or extracting solvent, and C is soluble both the components or both the solvents. So it is called solute. So this we are interested in removal of the C. So Now the compositions, three compositions are there, then we call this a ternary system, because there will be three different components A, B, C, then we will call it as a ternary. So ternary mixture, its compositions. Suppose if I give a mixture of A, B, C to you, then that mixture can be represented in a triangular diagram only, because it is having three components. So the triangular diagram, which is a equilateral triangle, and each side will be divided into the equal parts, then the apexes, that means corners, are showing the 100% of the pure components. For example, if I give a mixture and it is having uh, the compositions which are falling here, the point is falling in this corner, that means you should say that the A is very high and B and C are negligible. So if you go to the corner, A is 100%. Similarly, if it is falling here, a point, then you should say that B is 100% and C and A are in negligible quantities. If you are looking at this corner indicates 100% of the B. Similarly, this corner at the top apex is 100% of the C. And this side BC represents the mixture of B and C, mixture of the C and B. So you can just see 1 minute.
This conference will now be recorded.
So this diagram represents the ternary mixture, and if I take a point here, see B, here this point is called K. Okay, so this point will be having 40% C, that means vertical heights will indicate the C composition. Then this side 20% of the B, and this is the 40% of the A. So if you are coming down, for example, you are having a mixture of B and C. When you are on this, then you have a pure when mixture of the B and C only you will be having. And while you are going into this, then the A composition, A is 0 here, A composition go on increases, and while you are coming here, B and C will reduce, and when you come to this corner, then B and C will become 0, it will become pure A. Similarly, this is the C. When you are coming down, so it will be having A and B, and it comes down to base of the equilateral triangle. Base will have a mixture of A and B in which there is no C available. Similarly, this side also, this side indicates, AC side indicates the mixture of A and C. So here 80% of C and 20% of A. When you come down here, your composition of the A and C will be reduced, and then when you come to this side here, then you can say that A and C will become 0, and it is a pure B. So it is like that you can able to uh, represent a single point of a mixture which is having three components. If you put here another point, then it will have this much of C and this much of A and this much of B. Like that you can draw the mixture points at a different uh, locations in the equilateral triangle. So that is how you can able to draw. Now if you take a particular mixture initially when you add A and B, then a certain A will be miscible with B and certain B will be miscible with A, or you can say that A is completely pure and B is completely pure, but upon the addition of the C, then they will be having three different components, and these three component they will be mixing together, and they will form either homogeneous phase or heterogeneous phase. So if I take a mixture point which is falling here, so that gives only homogeneous phase. That means it will be in a single phase forever. It never split into the two different phases. But if you are looking at this curve, and here if you take one point, your mixture point after addition of the C and A and B, if the mixture point is falling here with this much of C and this much of A, this much of B, then it will be having heterogeneous nature. What do you mean by heterogeneous nature? After some time, the mixture will be settling into the two different layers. So two different layers means each layer will have again ABC in a different proportions. So the mixture layer which is having more A will come this side, the mixture which is having more B will come this side. So this can be added as a line which is called tie line. Tie line. So this tie line is the equilibrium line, and which will be joining the two equilibrium composition mixtures. This is a one layer which is A rich layer. This is another layer B rich layer. So both will be added by tie line. So you can draw such tie lines, and this curve which will be demarcating the homogeneous nature and heterogeneous nature is called binodal curve. So you have such a binodal curves for different systems. You can't say that for all the binodal curves will be like this. Some binodal curves will have a different structures and different loop areas. So this is having this much of loop area, and it is having so many tie lines. What this tie lines indicates? Tie line indicates that if you are just taking the mixture like this, see, if you take the mixture like this, MD, this is a mixture point, then this mixture has to separate or has to divide into the two distinct phases. One is this phase, raffinate phase, another is extract phase. Raffinate phase is feed solvent rich, and extract phase is organic solvent rich. Then this is called tie line. Why it is called tie line? Because this will be this equation will be valid. What is this equation? R by E is equal to line ET, means ET this height minus line MO this. So this minus this divided by line MO minus line RL. So this will be equal to the composition of the solvent in the extract minus the composition of the solvent solute in the mixture divided by mixture composition minus raffinate composition. So the weight of R divided by weight of E will be equal to this one, because it will be a tie line. If this is not valid, then this can't be called as a tie line. For example, if you draw one line like this, so it will not be followed. So that is not a tie line. So tie line says that R by E is equal to, as per the lever arm rule, this EP, line EP means this one divided by line PS. So that means this by this, and line ME. What is the line ME? This one divided by line RM. So this will be applicable for the all tie lines. So whatever tie line you draw, these tie lines will be indicating the liquid equilibrium compositions. So instead of that, you can also draw this type of curve. So where you can avoid the triangular plot, you can draw only ordinary graphs. So I'll explain these ordinary graphs a little later. So before that, you please understand that I think you, in the process calculation also, you might have drawn these triangular plots. These triangular plots are very, very useful, and which will give, if two systems uh, are splitting into the two different layers with the help of another system. That means there are three components in a single system, so that can be represented on ternary graph. Okay, so here you can just see that the mixture which is having three components can give one single point on the ternary graph. So you can see different such type of systems. For example, if you take water, and which is having a acetone and will be separated by the chloroform. So water is a aqueous layer and chloroform is a organic layer. This is the feed solvent is water, organic solvent is chloroform, and acetone is the solute in between these two. So that is a example for the systems in which A and C, that means water and acetone, B and C, chloroform and acetone, two pairs are completely miscible. That means acetone is completely miscible in water, and acetone is completely miscible in the chloroform. But however, one pair, what is that pair? Water and chloroform. Water and chloroform is partially miscible, so they don't mix completely. So that is the way you are getting this type of curve. This type of curve you will get, and see that A to L, in this curve A to L indicates the partial miscibility of B in A. Similarly, B to K, this small gap indicates the partial miscibility of A in B. So here if you take, let us say this is a 95% of the B and 5% of the A. That means 5% of A is miscible in the chloroform. Similarly, if you take this is a 3%, let us say. So 3% of chloroform is miscible in A. So that's why you will get this point. For example, this curve starts at corner. That means there is no miscibility of B in A. And similarly, if it starts at this corner, you can say that there is no miscibility of A in B. So here you should understand that there is one pair is having a partial miscibility. That is A and B are having partial miscibility. And whereas A and C, there are no lines starting from this side. So that means A and C completely miscible, and C and B also completely miscible. So for such system, you can draw this line. This curve is called binodal curve, which is also called the solubility curve. So solubility curve means, and you can say that if A and B are taken at this position, and in which C is there, more C is there, then you see it is a homogeneous layer. In that, if you just add some more C, and it will go in upward direction, that means there won't be any second layer visible if you go on adding the C. But if you are go on adding either A and B, so this point will slowly come down like this and enter into the this zone. So this zone gives the heterogeneous nature. Similarly, if you add in this point only B, so it will be A, it will be increasing in this side and enter into the this zone. So it will again give you the heterogeneous zone. So to have the heterogeneous nature, the C composition should be less in the mixture, such that it will be falling under the binodal curve. So in the binodal curve again you have a tie lines. So these tie lines can be extrapolated on X and Y. X is the weight of the C in the raffinate, that is the aqueous layer. Y is the weight fraction of the C in the extract phase. So you can just draw like this, and again you will get XY curve, which analogous to the XY curve of your distillation. So you can just convert this into this one, and see here in this case the tie lines are not having uniform slope. You should understand that it is not having uniform slope. They are not parallel lines. So at low concentration of the C, you have one inclination of the tie line. If the C is go on increasing, the inclination of the tie line also get increases. The slope of the tie line get increases, and finally it reaches to a point at which the width of the tie line disappears. The tie line will become a single point. So see here, the tie line has become a single point if you go on seeing, and this is called a plight point. So plight point is a point at which there won't be a tie line. Tie line width is 0. Okay. So if you have a mixture, at this composition, plate point composition, like this much of C and this much of B and this much of A, such mixture is unable to separate. It is very impossible to separate by using the liquid extraction. So you should understand such that at a plate point the separation is not possible. Separation is not possible, and also we'll put in a separate term once we discuss further. So another term will come for the plate point, and right now you can understand that plate point is a point at which the tie line becomes 0. Tie line disappears. You can see here also, I have drawn in ordinary graph. You can see the tie line becomes a single point here. So it is having x is equal to y. So therefore the separation is not possible. But however, at a particular temperature, if you find a binodal curve of this nature at low temperature, if the temperature increases, the binodal curve area decreases. Binodal curve area decreases. Why it is decreasing? And you can say that the effect of the temperature on solubility. Effect of the temperature on solubility, if you see that the temperature increases, the solubility of the solute in the liquid phase increases. So A solubility in the B as well as C solubility in the mixture increases, then the binodal curve area decreases. So this is the lowest temperature you find like this, and highest temperature if you go, then you will have very less binodal curve. That means heterogeneous area decreases when the temperature increases. Okay, so at lower temperature you can see more heterogeneous area. At high temperature you are having very less heterogeneous area, whereas homogeneous area is very high. All these compositions above this curve are showing you only homogeneous phase. So we require to have heterogeneous phase. Therefore high temperatures are not suggestible for the liquid extraction. You can do at low temperatures. Okay, so this is the one type of phase diagram which results. So the example is water, chloroform and acetone, and you can also cite another example, water and acetic acid, chloroform can also give like this, and water, acetic acid and benzene also will give this type of so there are number of such type of systems, but how to choose the which solvent is to be used, we'll discuss later. And similarly you can see in the second type of the liquid equilibrium, here you can say that one pair completely miscible or two pairs are partially miscible. So you see here the system of the three liquids A, C, B, and AB and BC partially miscible. You can take an example of the chlorobenzene, water, methyl ethyl ketone. Chlorobenzene, water, methyl ethyl ketone. In this case, if you take A and B, chlorobenzene and water, that is a feed solvent and extract solvent. Here water is the extract solvent and chlorobenzene is the feed solvent, in which C is contained. By using water, we are washing this liquid. So A and B and similarly B and C are partially miscible, whereas A and C are completely miscible because they are available in the feed. That's why we are unable to separate. So A and C completely miscible. Two pairs AB, BC are partially miscible. If such a system is taken, then you will get this type of binodal diagram. Binodal diagram changes. There is no plate point here. These are the tie lines. You can understand. There are two lines. These two lines, in between the two lines there is an heterogeneous area. Outside of this will be homogeneous and outside of this will be homogeneous again. So that means if you have a point here which is having ABC, chlorobenzene, water and methyl ethyl ketone, you are having here, that means below this line, then it is not possible to split into the two different layers. Similarly, if it is having here, it is not possible to split into the two layers. If it is at M, then it is splitting into the two different regions. So you will get here, this indicates the miscibility of B in C, and this indicates the miscibility of C in B, and this small area indicates miscibility of B in A, and this indicates the miscibility of A in B. So you are not having any such type of immiscibility between A and C. That's why we call this system as one pair completely miscible, two pairs are partially miscible. Such systems are subjected to do the separation uh, in a different way. See, the XY diagram will result. There you have got in a upward, and here you are getting below this XY diagram. But here there is no plight point. There is no plight point in the this thing. So what we do is, such system we will increase the temperature. When you increase the temperature, then you see typically the solubility of C in B and B in C increases than A and B and B and A. So this type of system may be possible at higher temperature. So this is at lower temperature you have found. So we are having some trouble to use this diagram for the estimation of the different parameters for particularly chlorobenzene, water and methyl ethyl ketone separation. Then we will do at high temperature. Then high temperature you are again having this type of curve. So which resembles the actual binaural curve, and which will be again having one plight point. So like that they can be subjected to the at high temperature, but certain systems are not at all required. And similarly, you can see another example: naphthalene, aniline, isooctane. So this system, if you take and naphthalene will be usually at different temperatures. The temperatures are typically low. It may also in the form of solid. So two partially soluble and one solid will give this type of typical diagram. This diagram indicates that you are having a heterogeneous within this binodal, and if you are here, then you have no homogeneous, and here you have a homogeneous. Above this you have one solid. Certain naphthalene will be in the solid form at high concentration, and aniline and octane will be in the liquid form. So there will be three different layers here. So such systems are having a limited possibility for the separation. Only this much possibility is there. Above this concentration of the naphthalene, the separation is not possible. So you have to look at the solvent which you are using. So usually we use a different notation scheme, that is A and B. As I told, A and B uh, are pure substantially insoluble liquids, and C is the distributed solute. Mixes to be separated by extraction are composed of A and C, and B is the extracting solvent that I have already explained. The same letter will be used to indicate the quantity of the solution or a mixture and the location of the mixture on the organic phase diagram. For example, if I indicate A, that means it's a pure A on any diagram. If I write B, that is a pure B on the diagram. The quantities are measured by the mass of the batch operations, mass per unit time for a continuous operation. So per continuous operation, we use mass per time. Otherwise, we use mass. That means kgs we use for the batch operations. For a continuous operations, kgs per hour or kgs per second, like that we use. Okay, this is a certain notation which you are going to use in a coming the discussions. When you use E, that means mass per time of the solution, E, an extract. E is the extract. So if I use E means mass flow rate of the extract, shown as a phase diagram by point E. So that will be shown generally with E. So R is equal to mass per time of the solution, R, a raffinate. So this is a raffinate. So you don't think that E will be having only B. Okay, E will be having A component as well as C component, and B component will be more. So that's why we are calling it as a extract. Otherwise, other two components will also be there. In the R, which is designated, R is designated for raffinate. This will also have the B component as well as the C component, but at a little quantities. So that's why it is called raffinate, shown as a phase diagram by point R. So E and R, wherever you find, just remember that E is extract and R is raffinate. Until unless it is specified, they will have all two components. That means three components will be there in E, and three components will be there in R. So another one, B, if you indicate with a B, B is equal to mass per time of the solvent B, solvent free, B free, quantities are indicated by primed letters. Primed letters means B prime, like that. So B is the total solvent which is used in the system. If it is batch process, if it is a continuous process, B is equal to mass per time of the pure solvent B. So you should indicate the solvent flow rate with B. And these letters also used in certain cases. E prime means B free solution per time, means in the solvent except B, whatever quantities are there, A plus C, which are moving along with the extract, will be indicated with the prime. So prime indicates solvent free coordinates. So R prime, E prime, so those indicates that one. And then X, X is the weight fraction C in the solvent, weight fraction of the C. How do you calculate the weight fraction of the C? Weight of C divided by weight of A, B, C. If all are there, you should take that. Okay. Weight fraction of the C can be calculated as weight of C divided by weight of the total, that thing, total solution. A rich solution, A will be more, but however B and C will also there. So you can calculate in that way. Y is also weight fraction of the C in the solvent, and X prime, Y prime indicates mass C divided by mass of non-C. Except C, whatever is there, that can be indicated, and find out the X prime. X prime is equal to X divided by 1 minus X. That is in the raffinate we will use X value, whereas in the extract we use Y value. So X prime, Y prime indicates the mass fractions of C on non-C basis. And then what is capital X? This is the weight fraction of the C in the raffinate liquid on solvent free basis. Usually we exclude the solvent, mass C divided by mass of A plus C in the raffinate. Similarly, capital Y is mass of C divided by mass of A plus C, in which we are not taking the B quantity. Therefore, they are called solvent-free coordinates. X and Y are called solvent-free coordinates. Then another thing, N is weight fraction of the B on B free basis. B means solvent. Solvent free basis, if you estimate the weight fraction of the solvent without solvent, it means suppose if you take the extract, in that extract you have all B, A, C. So you just exclude, take the only A and C and find out how much of weight is there of the solvent uh, on a solvent free basis. So you can calculate mass of B divided by, in the bottom you have to take only mass of A plus mass of C. Here B don't include. So in that way N will be calculated. So just remember this notation, because this notation will be used when we are discussing the process principles of the extraction. Okay. So we can also draw this. I will explain later. Let us focus on the how solvent will be selected. I think this is very important, and let us stop here. So in the next class we'll start from this concept, because I have to go for another viva which is conducted in the college. So I will explain this in the next class. So meanwhile, whatever I have explained, you please go through that and study it. Okay. Stop the recording.